Now, just like in single variable calculus, we've got this differential approximation formula based on the definition of derivative. Recall that the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So in the limit, as long as delta x is small, then these two quantities should be equal. So I'm going to sort of take out the limit and rearrange this and solve for f of x plus delta x. So that says as long as delta x is small, then f of x plus delta x should approximately be f of x plus delta x times f prime of x. So this is the one variable differential approximation formula. Well, the same thing holds in functions of more than one variable, and this is that f of x plus delta x, y plus delta y. As long as delta x and delta y are fairly small, this should be approximately equal to the starting point plus the partial of f with respect to x. Let me write that out. The partial of f with respect to x times delta x plus the partial of f with respect to x delta y. This should be approximately equal. Now if we move this f of xy over, this says that f of x plus delta x, y plus delta y, minus f of xy should be approximately equal to these two terms over here. The two partials times the differentials. Partial of f with respect to y, delta y. And this thing on the left is just the difference between the z values. So this is just delta z. So delta z should be approximately equal to this quantity over here. And this gives us the differential approximation formula. This says that dz, well, we'll define dz to be this approximate difference. It'll be the partial of f with respect to x times delta x plus the partial of f with respect to y, delta y. So for example, let's say we've got z equals x y squared, and we want to find dz. So dz we'll take the partial with respect to x, which is y squared times delta x, plus the partial with respect to y, which is 2xy delta y. So what this is telling us is it's an approximation for the error in our function if we move the x and y values a little bit. So let's see the example of this actually in error analysis. Let's say we've got a cylinder. So the volume of the cylinder is the area of the base. If this is a circular cylinder, it's going to be pi r squared times the height. And let's say we have these two quantities measured. We know that the radius of the cylinder is 2 centimeters plus or minus 0.1 centimeters. And the height is 7 centimeters plus or minus 0.1. And we want to find an estimate for the error in the volume. Well, according to our differential approximation formula, dV should be, well, we take the partial with respect to r, is 2 pi rh delta r, plus we take the partial with respect to h, and we get pi r squared delta h. Then we're going to plug in our quantities. I know that r is 2, h is 7, so r is 2, h is 7, and now the deltas, this plus or minus 0.1, this is actually delta r. It's the amount by which our r measurement is actually off from the true radius. And this plus or minus 0.1 is our delta h. So we plug those in, and that says that our dV is 2 pi times r, which is 2, times h, 7, times delta r, which we have as 0.1, plus the other term, and this is pi times r squared, so this is 2 squared times plus or minus 0.1. And then if we simplify this, up here we've got 14/28, so 2.8 pi. And in this last term over here, we've got 0.4 pi. So we add those together and we get plus or minus 3.2 pi. So that tells us the potential error in our estimate based on the differential approximation formula. Now there's a theoretical aspect on this this differential approximation formula, and that's the concept of differentiability. And differentiability is much like it is for a function of one variable. Remember that we say a function is differentiable this is now a function of one variable, if it is well approximated by its tangent line. So what that means is, so we've got this function over here, and we've got its tangent line. That says as long as the x values are close to our starting point, the function value should be close to the tangent line. And that's the same idea holds in functions of more than one variable, although instead of tangent line we think of tangent plane. So the way we formally write this out is we say that f of x plus delta x, x plus delta y, is close. So this right here is what our starting value was, so that we can think of that like this, the height right here. So it's going to be this plus, well, here we're going to actually use the differential part. We go back and look at our definition, and it should be these two partial derivative terms. So this is the partial of f with respect to x, delta x, plus the partial with respect to y, delta y. Now this is not going to be equal, it's going to be close. So we're going to add on these two extra terms, epsilon 1 times delta x plus epsilon 2 delta y. So this is giving us the error in the x direction and the y direction. So this differential formula holds as long as epsilon 1 goes to 0 and epsilon 2 goes to 0, as both the deltas go to 0. So let's maybe look at an example of this. Let's say we have the function f of xy equals x y squared. And we want to show this is differentiable by using that differential approximation formula. So we need a few terms on here. First, if we look at the formula, we need the two partial derivatives. So fx is y squared, fy is 2xy. So now let's expand out this f of x plus delta x based on our function. So f of x plus delta x, y plus delta y. We'll plug those in for the x and the y. So we've got x plus delta x, y plus delta y squared. And we'll go and FOIL this out. And this gives us x plus delta x times, now over here, we've got y squared plus 2y delta y plus delta y squared. And then we'll distribute this through again. So we've got xy squared plus delta x y squared. That takes care of the y squared term. Plus 2xy delta y. That was multiplying our next one through. Plus 2y delta x delta y. And now we'll take care of the delta y squared. So this is x delta y squared plus delta x delta y squared. So that was just the first term in this, the foiling out of f of x plus delta x, y plus delta y. And now the next part in our formula is that this should be equal to f of xy, and f of xy is this term right here. So this is f of xy plus the next term up is the partial of f with respect to x times delta x. The partial with respect to x times delta x, so that's this term right here, is fx delta x. And the next term up is partial of f with respect to y delta y, which is exactly what we have here. So it's the next term up is fy delta y. And then we've got a couple terms over here that should involve the epsilons, the things that go to 0 as long as delta x and delta y go to 0. Now there's more than one way to group this. So I'm just going to take the first two. So these two terms right here, if we factor out a delta x, this looks like delta x times 2y delta y plus, we just take the first one. So delta x times 2y delta y. So this is going to be the epsilon 1. It's the thing that's multiplied by delta x. And as the deltas go to 0, this term goes to 0. That's good. Now in the last two, we can factor out a delta y. And what we're left over with is x delta y plus delta x delta y. So this right here is going to be the epsilon 2. And as the deltas go to 0, this term goes to 0. And that shows that this function is differentiable. So f of xy is differentiable. because it was well approximated by its tangent plane. Now this idea holds in functions of three variables in much the same way. We say that a function is differentiable if f of x plus delta x, y plus delta y, z plus delta z is equal to, well, our starting value, f of x, y, z, plus the partial with respect to x times delta x, partial with respect to y times delta y, partial with respect to z times delta z, plus delta x times epsilon 1, and delta y times epsilon 2, and delta z times epsilon z, where the epsilons, epsilon 1, epsilon 2, epsilon 3, all go to 0 as delta x, delta y, and delta z go to 0. So now this is just sort of a formal, almost a proof that functions are differentiable. And so we're not going to spend a whole lot of time focusing on this, but that's the concept of differentiability.